Hi, how's it going? I'm Ian, and I'm the project lead for the solar stove design, senior design group. And this is a relatively new project. I was on board only this quarter, so for the past 6 weeks. And yeah, before we go ahead, I'm going to let my colleagues introduce themselves here.
I'm Jared.
I'm Laszlo.
Yeah, and like I was saying, it was a relatively new project. Me and Jared came on during the first week of winter quarter, but Laszlo joined this maybe week 4. And yeah, it's been interesting, it's been a little bit fun, but a lot of research. And I'm gonna pass this time to Laszlo.
Alright, so let's start with a little background. In majority of developing nations around the world, the method they choose to, or I guess they're allowed to, or have the ability to cook food with is the 3-stone fire. It's essentially 3 blocks of concrete, wood, some sort of biofuel that burns. It's an open fire, no ventilation. It's generally done inside of their huts or wherever their living quarters may be. According to the WHO, unfortunately, because it is an open flame, about 4.3 million deaths occur in 2012 due to this type of cooking. So our motivation. There are several types of cook stoves that have been designed and developed to combat this issue, majority of which are still use biofuels as the main medium to cook with. As you can see from this study that was done at Berkeley, open fire, the particulate matter is significantly higher than the EPA standards. And the improved biofuel cook stoves, which do exist, are improved but are still significantly above EPA standards. The only type of stoves that emit zero carbon monoxide or particulate matter are solar stoves. Unfortunately, this arena is not very much research. There are a few out there on the market, a few cook stoves. They're generally very expensive because of the technology. And more importantly, solar cook stoves don't really have, there hasn't been much design done for the energy storage. So generally just cook stove without the storage. So what we're trying to do, our main goal is develop a solar cook stove with energy storage capabilities. And our objective is to complete and improve upon the current design which has been done in the past years. So some of our constraints that we started out with, because I guess our customer base, we can call them, is in developing nations. Cost is essentially the biggest factor. They don't have much money. They can't go out and buy an expensive cook stove. So we want to keep it around $40. There's weight restrictions, as you can see. We need to have a minimum of 200 degrees Celsius at the surface temperature. We want to get 100,000 watts of energy to the cooking surface. We want 4 hours of cooking time, 4 hours recharge time, 18 hours of storage. We want it to last about 10 years and no maintenance. Once again, because these are developing nations, they don't have access to tools to fix their stove, etc., and they don't have the funds to do so either. This is just a little schematic of how exactly a breakdown of how it works. You have the solar collector. This is from previous years, this cook stove. The solar collector is what essentially gathers thermal energy. Then it's transferred to the storage medium, which is a storage vessel which contains a salt that melts, and at that point it stores the heat energy for about 15 hours, I think. And then that's the storage method, and then transferred to the cooking surface. So yeah. And then this is basically the breakdown of who did what.
And thank you, Laszlo. And I was placed in charge of a solar concentrator, and basically this is how it looks like. The only thing we have right now is the humongous dish right there. It's about 2 meters long. And so the first week I was sitting down with my advisor, and he wanted a different approach this quarter. He wanted us to basically characterize the reflector into equations, so we could do theoretical analysis before we build a stove or a reflector. And that was what I did for the past couple of weeks. And yeah. And my goal for the solar collector is to just provide as much heat as possible from the sun. And like I said, I spent the past 3 weeks studying various like solar tracing, solar, how the sun works, and so forth. And I spent the first 2 weeks playing around with the solar reflector, and I had a heat flux sensor, I had thermometers and stuff, and we had some fun lighting up, wood and seeing if you could burn it and stuff like that. And we found out that it was really sensitive to the position of the sun and so forth. Like in a span of 5 minutes, we had to move the collector in like different positions to gain maximum heat. These are some of the variables I spent about 2 weeks looking through like graduate studies material about view factor. Sorry, the equation's not up there, but yeah, these are some of the variables. And I came up with this equation, and I'm going to try to put it to the test. And last week, after our experimenting process, we had decided to complete the structure. Like I said, we only had the dish itself, so we decided to build the structure next quarter and mount it and actually get like actual data.
Okay. So I'm in charge of the salt vessel, and basically what the salt vessel is it's responsible for storing the heat or the energy, which we will be using to cook food with. And so the overall goal for our salt vessel is to maintain or minimize our heat loss to 5% in 18 hours. So our power output would be 1,000 watts for 5 hours, which is equivalent to 5 kilowatt hours. And so the constraints was I would have to minimize the loss or the max heat loss the maximum heat loss would be only 14 watts allowed in order to maintain that goal of 5% in 18 hours. And so the constraint was also the temperature difference between the cooking surface and the actual and the ambient air would be about 210 degrees Celsius, which came out to a total resistance about 15 meters squared times Kelvin over Ross. And so in order to do that, we had to look at different types of installations available. These are just a list, a couple of viable installations I looked upon. The most viable one would probably be wool, especially for third world developing countries, in terms of just the availability of it due to like the amount of livestock. There are livestock and sheep that are there. And also, a disadvantage in that is that wool is pretty flammable. So whenever it catches some of the heat from the solar collector, it can catch on fire pretty easily, and it smells pretty bad. But on top of that, I explored different types of installations too, such as styrofoam. The most common one used for houses is also fiberglass. But these two installations may not be as cost effective as wool, or as viably available as wool. And so upon elaborating more upon the vessel, I looked at different geometries as well. So one of the geometries was a spherical geometry, and how we looked at what happens if we hold the thickness of a sphere constant and vary the different lengths of the radiuses as well. And so as you see in the figure right there, as we hold the thickness of the sphere constant and we increase the radius, we see like a linear geometry, linear graph or a linear trend in where the resistance begins to decrease as the radius increases, and same vice versa when we hold the radius constant of the sphere and vary the thickness, we see that the resistance increases. And so similarly, I did that with the cylinder geometry as well. We looked at holding the thickness constant and seeing how the resistance changes with varying radiuses. As you can see, it decreases in like a parabolic geometry, while if we held the radius constant and varied the thickness, the resistance would increase increase significantly. And so what's next? We can explore just different types of alternatives in terms of insulation, whether it might be vacuum and just radiation heat transfer, and also just different methods in constructing a new vessel, and more cost analysis into how viable this is in building.
So my colleague Alvin couldn't be here today because he had other obligations, so I'll attempt to be an expert on solar tracking. But so Alvin spent the past 4 weeks doing research on different solar tracking. He told me about he contacted a professor up in UCLA and he talked about passive tracking with him, and he was in charge of different bearings and stuff. For that professor ran a company, and he does. I forget, but it was a bearing system for passive tracking. And the objective for solar tracking is to basically find, to determine if solar tracking is viable and cost effective, or is it worth it to have solar tracking on our system. And yeah, and the solar tracking that we're talking about is passive solar tracking, so it means that it does not have electronics. And how that works is we use a liquid called Freon 12, and this liquid is special because it has a really low boiling point, and basically you insert it into our surface, and when a side of the material is heated, it vaporizes, and this side would be lighter, so the surface would tilt into that direction because other liquid would flow into this direction. So that's the simple gist of how solar tracking works. And here are some things that you consider in his calculations. For example, he found out that the sun does not always track in the same trajectory, maybe because the Earth is spinning in a different, always in a different course, and so we have different, so these are just some of the considerations taken into for his calculations. Just the illustration of the sun location in terms of our seasons. And here are some of his equations that he has determined. And the possible design, like I said, was Freon 12. However, the only factor that's, it's an advantage to use solar tracking. However, it's the only disadvantage for this system is that it costs too much because of the Freon and the setup of the system.
All right, I know we're kind of running short on time, so I'm going to do this as fast as possible. So I was basically the conduit guy, transferring the energy from the salt to the cooking surface. The current design essentially, so this is a sphere, right? It's a truncated sphere. It's a sphere with a flat top. There's a thermal fin sticking into the center of the sphere, which basically conducts the thermal energy from the salt up to the surface. This is the current design. So my goal was to optimize the design because from what I read from their research, as you can see, the length of the fin currently is 3 inches and diameter is 1.75 inches. The numbers, I don't know where they got them from. So my goal was to, along with the master student, Michael, who we're working with, to basically optimize the fin diameter and also look at alternatives such as heat pipes. Next slide. So essentially what I was tasked with doing is doing a very basically bare to the bone, simple kind of just a baseline calculation, something to compare everything to. It's just a 1D conduction model, assuming that the sides are adiabatic. The metric we're using is essentially the resistance. We're going to vary length and area, keep the conduction coefficient constant at aluminum, because that's what we're using. That's between aluminum and copper, but we chose aluminum. Go to the next slide. So there's some of the results. Length, resistance varies linearly with length, and then resistance varies exponentially with fin diameter. Go to the next slide. Essentially what we got from this was that length essentially has very little effect on the resistance of the fin itself. What dominates is going to be the diameter. So just in the length, regardless if we have a 1 inch or 7 inch, it's negligible. What we're really going to want to focus on is adjusting the diameter of the fin, and then optimizing the tube, essentially. Future work, 2D thermal model, make it more accurate, taking into consideration transients, and then percent of total sphere volume allocated to fin, so basically a trade-off between salt and fin size. One more slide. And then heat pipes, we also looked into this. This was more just research, understanding how heat pipes work. Essentially, heat exchanger, there's a working fluid within the vessel. The liquid fluid absorbs heat from the salt. Difference in vapor pressure causes the vapor to rise, where it is released to the ambient air to the cooking surface. It condenses and then drops back down via capillary action to the fluid, and the cycle repeats. I was initially
2 minutes.
Okay, I was initially going to do this by designing from scratch, decided to not do that and instead look for commercial heat pipes that fit our constraints. So we're purchasing that probably next week, and then going to do some testing.
Oh, yeah, that's all.
Okay, cool.